Okay, we're going to continue on here into organic chemistry, I think, and don't need that. Don't need a calculator. So we're getting into these chapters of organic chemistry where really there's no calculation. There's just some drawing, some equations, some naming, and that type of stuff. And again, pretty much throughout the rest of the chapters for the semester, pretty much no calculations involved. We still have plenty of calculations from our previous chapters, but starting now, pretty much not too much. All right, so let us talk about this, which is organic chemistry. Pretty much the study of organic chemistry, or really kind of the first sentence in any organic book that you come across, is pretty much the study of carbon and carbon-containing compounds. So the basis of all organic chemistry is carbons essentially attached to carbons, and attached to those carbons are hydrogens. So that is really the basic setup of most organic compounds, is pretty much that connection of, like I said, carbons to carbons, carbons to hydrogens. As we go through the different sort of organic chapters, we will find some differences in these type of compounds, and really we'll kind of substitute out, for example, some of the hydrogens for some other elements, and that'll give us different types of organic sort of compounds that happen. As you can see here, organic compounds, typically because they contain this, they really do contain, mostly in a lot of cases, non-polar bonds. So our carbon-carbon bond is non-polar, as they would share the same electronegativity value, like we talked about when we were doing bonding. Also, if you remember, the carbon-hydrogen bond has a difference in electronegativity of about 0.4, which is also pretty much the cutoff for a non-polar bond. So most organic compounds are going to be non-polar. There will be some organic compounds that will be polar, and as we'll talk about as we go through these different compounds, what's going to mostly happen in the case of organic compounds is you will have a part of the molecule that is non-polar, a good part of it, but there will be a small little part of it that is polar, and that's what gives it some of its polar attributes. So in a compound such as this is definitely going to be non-polar, all the carbons and the hydrogens together. Organic compounds, as I mentioned, is carbon, and it's really important when we talk about carbon. Carbon has 4 valence electrons. The most important thing when you think about carbon is it pretty much wants to make 4 bonds, and that's a really important thing to keep in mind as you go through organic chemistry. Is carbon pretty much needs 4 bonds to reach the octet rule, like we talked about with bonding. It should never ever have more than 4 bonds though, and I say that because commonly when people start drawing organic compounds, they like to just keep on drawing lines until they're out of lines, and then maybe they put dots on it as well. But again, it can only have 8 valence electrons, like we talked about with bonding. The octet rule, only 4 lines. Pretty much 99% of the time with carbon, it's going to be a bond. So you very rarely, there are a few instances or so, but you very rarely have non-bonding electron or dots on carbon. So they're mainly bonding electrons, lines, like where we drew our Lewis structures. With that in mind as well, as I mentioned, we do swap out some of those hydrogens for other compounds. So we'll see some oxygen-containing compounds, sulfur, nitrogen, and the halogens like to get in their group 7 as well. Why we're talking about bonds and no more than 4 bonds for hydrogen also brings up a very good remembering of hydrogen should only have 2 electrons or 1 bond, right? So hydrogen should always be on the outside. In addition to people liking to put more lines on carbon when they're doing organic chemistry because it looks more chemistry like, I suppose, they also like to put like lots of bonds on hydrogen and dots all around hydrogen. Same rules apply as what we talked about when we did Lewis structures. Hydrogen can only have a maximum of 2 electrons, which means it should always be on the outside, should always have just one single bond to it. And again, carbon will make enough bonds to get to 4, which will give it 8 valence electrons. So those are two sort of bonding things that we talked about earlier. That definitely sort of comes back out here in organic chemistry, and you want to keep that in mind as we go through it. Because it is nonmetals and nonmetals happening here, carbons, nitrogens, oxygens, sulfurs, all those things, they have covalent bonds. So organic compounds basically share electrons. They have low melting points and boiling points, and they're really flammable and undergo combustion reactions, and they're not soluble in water because they are nonpolar. And nonpolar things, as I believe we might have talked about along the way, use what are referred to as dispersion forces. And dispersion forces are the forces that hold one nonpolar molecule together with another, and is what is known as a intermolecular force. And dispersion forces are pretty much the weakest type of force that you could have to hold together two molecules. The strongest is hydrogen bonding, which is a polar molecule with a bond between hydrogen and nitrogen, oxygen, or fluorine. That is the strongest intermolecular force you could have. Dispersion forces is the weakest. They are temporary forces that occur by electrons just kind of moving from one side to the next. A nonpolar molecule, if you remember, means that basically overall you have equal sharing of electrons over the entire molecule, which means it's kind of a neutral molecule. There's no positive side, no negative side. When you have a polar molecule, there is a positive side and a negative side. The negative side being where all the electrons are sort of hanging out because of the unequal distribution of electrons over the whole molecule. The positive side is where the electrons are not really hanging out. In the middle is dipole-dipole interaction in terms of strength, and that also is for polar molecules, but that cannot hydrogen bond. So that's the strongest. This is the weakest. So for example, when water interacts with another water, water is a polar molecule, oxygen more negative than the hydrogen, which is more positive. And when two water molecules come together, they work well with each other because basically the negative side of one is attracted to the positive side of another. And that is what is known as hydrogen bonding. All intermolecular forces and all how molecules interact with one another, they all interact with a basic interaction of positive and negative attraction. So that's how molecules basically interact with themselves and also with other molecules. Something like CH4, for example, which is nonpolar. It is essentially a neutral molecule, and it will use this dispersion force to basically attach to another nonpolar molecule. And what happens is because it's nonpolar, it originally does not have a charge, but something does happen to give it a temporary charge. So temporarily, this guy will have a positive side and negative side. This guy will have a positive side and negative side. And temporarily, they will be able to interact with one another through dispersion forces. It's temporary because honestly, if the electrons just move back one way or the other, they're going to kind of break apart that connection. They can't maintain that connection over a long period of time. So that very weak interaction between nonpolar molecules that use dispersion forces is why we see a lot of organic molecules very volatile. also in the gas phase. So if you think about a lot of the early organic molecules, things like methane, propane, butane, those are all gases under normal conditions. And that's because they're held together by these super weak forces, which means you just look at them wrong, they're just going to go off into the gas phase. It doesn't take a lot of convincing for them to do so. That's also why when we look at water, even if you look at it really strongly, it will stay together under normal conditions, right? Because it's held together by really strong hydrogen bonding, and that's why it's a liquid under normal conditions. So when these two guys get together, for example, that's why a lot of organic molecules are not soluble in water, because the organic molecule wants to use dispersion forces. Water, which is polar, wants to use hydrogen bonding. And those are two very different types of ways that they interact with one another. So what ends up happening is they can maybe interact for a little period of time, but eventually what's going to happen is they are going to separate out from each other. They're not going to be able to maintain that interaction over a long period of time, like oil and vinegar salad dressing, for example, right? You can mix it, and for the short period of time, it will mix. But as you leave the bottle, right, everybody starts to separate out from one another. The oil from the vinegar, vinegar polar, oil being non-polar. They don't really have a way to maintain that interaction over the long period of time. Also, if you've ever seen pictures of an oil spill in the ocean, the oil ends up floating on top of the water. And that's because, again, the water is polar, the oil is non-polar. So over a long period of time, they really don't mix, and it just kind of ends up floating, like we kind of see here in this sort of beaker. So they typically are flammable and go into the gas phase really well because of that weak interaction. That also means typically organic molecules, because of the dispersion forces, will have low melting points and boiling points, because again, they're not held together super tightly or strongly. It doesn't take a lot of convincing to get them into the gas phase. And what that means is they have very low boiling points and melting points. Something like water has a much higher melting and boiling point, because water with another water is held together by really strong hydrogen bonding, which means it takes a lot of energy to break them apart. And that means it's a higher melting point and boiling point than you would have with something using dispersion forces. Any questions on any of that there? So organic versus inorganic compounds. Inorganic compounds are our ionic compounds. So those are our metals and our nonmetals together. They typically will have high melting points and boiling points, and that's because inorganic compounds are held together by electrostatic attraction. That's a super strong intramolecular force, which means within the molecule. It's basically a fancy word for positive negative attraction. So ions are held together by that really strong attractive force between the positive cation and the negative anion. And under normal conditions, they do not sort of exist as gases because of that really strong force and that really strong and high melting and boiling point. We might have talked about it before, but typically if you take an ionic solid, like say sodium chloride, you could heat the heck out of it and it will just start melting because it is held together really strongly rather than breaking apart. Organic guys, like I mentioned, pretty much are held together very loosely, if you will, and able to go into that gas phase a lot easier. That's why a lot of organic compounds are said to be volatile, which means that they can start in sort of the liquid phase, but can very quickly enter into the gas phase really easily. That's why a lot of times when you're working with organic compounds, as I might have mentioned, they throw you in a fume hood because they give off lots of fumes and vapors and stuff like that, because they can't go into the gas phase really easily. That's why you usually want to be very careful if you have a Bunsen burner out and you have organics, because they are flammable and will go in the gas phase and can cause a fire, which you do not want. Here's a table from your book of some comparisons of organic versus inorganic guys. Again, organic nonmetals, carbon, hydrogen based. Inorganic metals and nonmetals, again, high boiling points and melting points for inorganic, low melting and boiling points for our organic guys. All right, so each characteristic most typical of inorganic or organic. High melting points is inorganic, yes. Is not soluble in water, is typically organic. Has a form of carbons and hydrogens, that is your basic organic setup. Has a form of magnesium chloride, that's a metal and a non-metal, which means it's ionic, right? Which means it's going to be an inorganic guy. It burns easily in air, that's going to be organic. It is the basis of combustion reactions that we talked about. So if you remember, an organic compound plus oxygen will make CO2 and water, which is a combustion reaction. Has covalent bonds, would also be organic. As inorganic, and our ionic compound obviously does not share electrons. Any questions on any of those there? All right, so let's talk a little bit about hydrocarbons. Hydrocarbons are pretty much what the name implies. They are carbons and hydrogens that are attached together. So when we look at a formula such as this is a hydrocarbon. It is the basic, simplest organic molecule you can have. That is CH4, which is methane. This is what is referred to as the molecular formula. This is what is sometimes referred to as the expanded structural formula. The expanded structural formula is pretty much like a Lewis structure where you draw out all the hydrogens, basically. This guy here on the bottom, and also the CH4, they're what are referred to as being saturated hydrocarbons. Saturated hydrocarbons means that carbon has, in that particular case, the maximum number of hydrogens it can have. So if you remember, we talked about carbon wants 4 bonds. So in the case of one carbon, the maximum number of hydrogens it can have is 4, and that means that it is saturated. In this case, this carbon here will have a maximum of 3 hydrogens, along with this carbon has a maximum of 3 hydrogens, and that's the maximum each of those carbons could have. And this would also be a saturated hydrocarbon. The carbons on the right there only has 3 hydrogens because the 4th bond is between the 2 carbons. Yeah, so that 2 carbons, right, have a bond between them. And that means that each of those carbons will only need 3 more hydrogens to get to 4 bonds. Essentially, in organic chemistry, here's the deal. Pretty much when you're out of elements, everything else is hydrogen to give carbons 4 bonds. So if you're not sure what else goes there, it's pretty much going to be hydrogens and the appropriate number of hydrogens to get carbon to 4 bonds, depending on what's there. So this is the expanded structural formula for this guy. C2H6 is the molecular formula. And another common formula sometimes used is this one, CH3, like so. This is the condensed formula. So what is the difference between the condensed formula and the expanded structural formula? Is you didn't draw up the hydrogens, basically, is the difference. So those are 3 common formulas that we see a lot in organic chemistry, in addition to line structure that we see, which kind of looks like this. When we have something like this, this is what is sometimes referred to as line structure. And in line structure, it is basically the simplest representation. So everywhere sort of a line ends, or everywhere where 2 lines come together, those are all carbons. So for example, here, This would be a carbon. That 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 would be a carbon. And that would be a carbon. So everywhere I put a blue dot, which is pretty much where the line ends or two lines come together, will make a carbon. I lost track there, but that's 2, 4, 6 carbons. So we basically have 6 carbons. Now, not usually drawn. You don't usually put the carbons in line structure. And also things that you don't usually put in line structure, the hydrogens, but there are hydrogens that's assumed to be here. So if we look at the hydrogen on the far right here, it has one line coming in, which means that carbon has one bond. And in order to get the 4, it would need how many hydrogens? 3 more. So there technically is 3 hydrogens at that carbon. The carbon next to it has 2 lines coming in, which means in order to get the 4 bonds, there technically is 2 hydrogens there. Same thing here, 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, and at the end, only 1 line coming in, which means there are technically 3 hydrogens at each of those spots. So we don't usually draw any of that stuff, any of the hydrogens or carbons on there, but as you can see, that little line structure there has, you know, something like maybe 14 hydrogens as well attached there. 3, 5, 7, 9, 11, and 14 hydrogens. So that little representation of up, down, up, down, up is basically 6 carbons with 14 hydrogens, and that's what's known as line structure. So those 4 sort of formulas are very commonly used in organic chemistry. Molecular formula, which basically just kind of tells you what's there. Structural formula, expanded structural formula, kind of like a Lewis structure where you kind of see all the bonds and definitely all the hydrogens happening. A condensed formula, sort of a shorthand of the Lewis structure where you don't draw out the hydrogens. And again, the line structure, which is kind of like their bare basic bone structure. And that's used again to represent things. Any questions on any of those different types of formulas? Everything that I drew is still, all these things are still saturated hydrocarbons. Basically, a saturated hydrocarbon is something that has all single bonds. And because they have single bonds, you have the maximum number of hydrogens that you can possibly get. So all these guys all have single bonds, no double bonds or triple bonds, and that will get you your saturated hydrocarbon. Methane, as we can see there, is again your simplest organic guy you could have. Here's a few different formulas. The space filling model, which is sometimes used on computers to kind of show you the different sort of densities of each of those. The ball and stick model, like you would take out your modeling kit and build it. This is our wedge and dash sort of model. And wedges and dashes mean, like, you know, the atoms going behind the page, the wedge kind of coming out from the paper. They sort of show the 3-dimensional. Expanded structural and are condensed in this case. It's kind of the same. For methane, since there's only 1 carbon, the condensed and the molecular formula are pretty much the same in that case because there's only 1 carbon. Ethane is the next important carbon compound. And by the way, all these guys are what are referred to as alkanes. And alkanes all have single bonds. And alkanes have a general form of CnH2n plus 2. So if we go back to our methane, CnH2n plus 2, there is 1 carbon, so N equals 1. 2 times 1 is 2 plus 2 is 4 hydrogens. So that's where we get our 4 hydrogens from. Here, carbon, our N is 2. 2 times 2 is 4 plus 2 is 6. So ethane, again, has the 6 hydrogens that are attached in this particular case. Methane, ethane, propane is the next one. And propane has 3 carbons, and again, would have a formula of 3 times 2 is 6 plus 2 is 8 hydrogens. So this is propane, which looks something like this in the expanded formula. And condensed would look something like this. And line structure will look something like that. Yeah, so all three of those guys are propane. These are all alkanes, which is the simplest organic molecules you could have. They all have single bonds. By the way, you might notice these are all alkanes, ANE. This is methane, ANE. This is ethane, ANE. This is propane, ANE, and here is butane, ANE, which is 4 carbons and 10 hydrogen. So the group of organic molecules that have single bonds are known as alkanes. They end in ANE, and that's how the names of the alkanes end as well. Predict the shape around each of these carbons. So let's talk about the shape around each of these. And this goes back to our sort of Lewis structure days. We will look at this here, and this guy has 1, 2, 3, 4 electron pairs, and it has 4 bonds. So if you remember, something with 4 electron pairs and 4 bonds has that tetrahedral geometry. That's that 109.5 degrees as you go through there. By the way, every single one of these have 4 electron pairs and 4 bonds. They are all tetrahedral, and that is why when you draw line structures for alkanes, they typically have what is referred to as the zigzag shape because of the geometry of that tetrahedral. This guy goes up, and down, kind of zigzag back and forth. Once again, what I just drew there is the line structure for butane, which has 1, 2, 3, and 4 carbons. And once again, the condensed formula would be CH3, CH2, CH2, CH3 would be our condensed formula. Again, that kind of zigzag approach that you see with a lot of line structures is because of the tetrahedral geometry that we find in alkanes. Because they're all single bonded, they all will have basically 4 electron pairs and 4 bonds and have that tetrahedral kind of geometry that makes it go that way. Any questions on that there? So alkanes, as we sort of been hitting to here, is a large number of carbon compounds. They all have single bonds. So when we talk about organic compounds, there's really what is sometimes referred to as the functional group. And the functional group is really the part of the organic molecule that makes it that type of organic molecule. So, for example, alkanes, really the functional group, although some people may not call it the functional group, is really the carbon-carbon single bond. So if you have a carbon-carbon single bond and only carbon-carbon single bonds, those are alkanes. And as I showed before, that is our CnH2n plus 2 is basically the general formula of how many hydrogens should go with our carbons in this case. This is hexane, which has 6 carbons. And again, it would have, that means that in this case, N is 6. 6 times 2 is 12. 12 plus 2 is 14 hydrogens it would have in that particular case. So the N in this case is the number of carbons, and you can multiply it by 2 and add 2 in the case of alkanes, and it'll tell you how many hydrogens you should have. Any questions on that there? So let's talk a little about alkanes and naming alkanes in a sense of what the first 10 alkanes are. When we go to name things, usually in our class, and in most cases in terms of organic chemistry, and one thing that we will see is in organic chemistry, there's lots of names for the same thing. There's kind of the official name, there's the common name, there's the historical name, there's the name Bob calls it, whatever it may be. So you can't call like the same thing 3 different things, and it's very common in organic chemistry that you come across that. For example, acetic acid is ethanoic acid. It's also known as vinegar, just commonly as well. So, the same thing could have multiple ways. Typically, when you're asked to name something in this class, you should name it through what is known as the IUPAC name. And the IUPAC name is International Union of Pure and Applied Chemistry. I'm saddened that I know that, but there's the three guys that basically come together and decide how you name everything with all the funky rules. You can send in your thank you notes to them as well. Like how we get the names on the periodic table, how we name things like type 1 and type 2 type stuff we talked about with naming, all the crazy stuff that we're going to name here in organic chemistry. So when you're typically asked to give the name, usually you want to give the IUPAC name. That's kind of like the formal name, the official name for that compound. And again, we'll see a lot of cases where, there might be more than one way of naming it. So when we look at naming alkanes, they are formed by a continuous chain of carbon atoms, and they are named using the IUPAC name, and alkanes will always end in ANE. When we talk about structures for organic chemistries, there's two types of chains we look at. So there is carbons all attached kind of in a row, and that is what is sometimes referred to as a straight chain. And pretty much like it looks like, it's like a straight line of this carbons attached to carbons, basically. There's also ways that carbons come together where there is kind of a straight part and then it kind of branches off into other spots. So you could have some carbons coming this way, and all of a sudden you got some carbons coming that way, maybe some carbons going that way, and obviously hydrogens along with it. So kind of like a tree, there's like a main sort of tree trunk there, and off of it are what are sometimes referred to as branches. And that's the idea here. This is what is sometimes referred to as branch chain. And that means, again, you have this kind of main long part that's kind of straightforward and straight across, but then off of it, like branches on a tree, you got things kind of coming off in some other directions. There's also ring type structures are cyclic. And those are where carbons, come together and kind of close in and make like a ring type structure where, it's not open. It's basically, kind of one end joins up with the other end basically and kind of closes it off in sort of a ring or cyclic type structure. So depending on sort of the type of chains and stuff that we see, it does have an effect, as we will see, on the way that you go about naming things. But those are different sort of ways that these carbons can kind of come together. Any questions on that there? All right, so the very first thing that you should learn is what's on this table. And that's really important because this is the first 10 alkane names. And the faster that you learn these names and their formulas, the more enjoyable organic chemistry will be for you, because pretty much everything else along the way all come back to these first 10 names. So everything comes back to these first 10 names. So you really want to make sure that you understand these names, how many carbons go with it, the formulas for it. Everything else that's named along the way is just like a slight little tweak of those names. And then that's how you sort of get to the name that you're looking for. So let's go through each of these here. And I believe the line structure is like one off on this chart. Maybe they fixed it in your book by now. But they all are like one off of the spot there. So they all kind of come down one here. I think they got moved. All right. So first off, we have one carbon, and that means we have 4 hydrogens. That is methane, ANE. We have 2 carbons, which means 2 times 2 is 4 plus 2 is 6. That is ethane, ANE. 3 carbons, that is going to give us 8 hydrogens. 3 times 2 is 6 plus 2 is 8. That is propane. 4 carbons. That's going to be 4 times 2 is 8 plus 2 is 10. That is going to be butane. And right around 5 carbons, we kind of roll into our prefixes like we use when we're doing type 3 compounds. 5 is penta, so this is pentane. Coming through 6 carbons, 6 times 2 is 12, plus 2 more is 14. That would be hexane. 7 would give us 16 hydrogens. That is heptane. 8 would give us 18 hydrogens. That is octane. 9 would give us a lot. 20 hydrogens would be nonane. And lastly, 10 would give us 22 hydrogens is decane. So these first 10 names here, you should definitely know, and the formulas. Here in this table, you can see the molecular formula. You could also see the condensed formula and the appropriate line structure. Again, I think it's kind of one off on the picture there. There's not really a line structure for methane because there's really just one carbon, so it's not much of a line. It's more of a point. So I guess ethane there would be the first one you could sort of draw a line structure for, since there's kind of 2 carbons in that particular case. Any questions on that there? Once again, these are all carbon-carbon single bonds. The attachment is the carbon to the carbon. And when we look at something, for example, like CH3, CH2, CH2, and CH3, this is the condensed formula. And just so we're clear, the connection is always, even though it's written like this, the connection is still carbons to carbons, even though in the expanded, it looks like the hydrogen is what's being attached to. So the proper connection, again, is that is CH3, that is CH2, that is CH2, and that is CH3 basically there. So sometimes people, when they see it in the condensed formula, they misunderstand that like the carbon's not attached to the hydrogen like it may look. It is always the carbon attached to the carbon. It's sort of the backbone of the molecules. But again, when we write it in sort of condensed formula, the hydrogens kind of get in the way there, and it might imply that they're attached that way, but they're not. So the reason we know they cannot be in the middle is, again, hydrogen should only have 2 electrons, which means they has to be on the outside. So that is definitely the connection that happens there. Question on that there. All right, so here again is our condensed structural formula. Each of the carbons is attached to the hydrogens, is written as a group. And again, here's butane. Sometimes you may have, in a condensed structural formula, you may have something like this, where maybe it is even shorthanded, if you will, there. And basically, this just means that there are 3 of those CH2 units repeating. So if you were to write it out completely, it would be 1 of these guys, 2 of these guys, 3 of these guys, and 1 more here, which means this guy actually has 5 carbons, right? And it's actually pentane. So you want to be careful if you are counting something like carbons, that you just don't go, it is propane, and miss the fact that you have that unit that's repeating. So that's, again, a shorthand that is sometimes used. Any questions on that there? There's our expanded, where really we just show the bonds to the hydrogen, and our condensed, we don't draw out our hydrogens there. There's our skeletal formula, our line angle formula. Sometimes people call it, but I call it, again, just line structure. Never usually you'll see the carbons written like it is there. It's just usually just the line. So if I had something like this, how many carbons does that have, and what is it? So this is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, and 7 carbons. So that would be 7 carbons. They are all single bonded because you don't actually see double bonds. They would actually be drawn in there as well if there were. That means that would be 7 times 2, which is 14, plus 2 more, which is 16 hydrogens. And as you correctly said, that would be our heptane in this case. Yeah. Again, at both ends, we would have 3 hydrogens, and then each of the carbons in the middle there would have your 2 hydrogens attached. Again, the idea here, just keep in mind, carbon 4 bonds. Yeah, so got to get it to 4 bonds. The only thing that you could add to pretty much get it to 4 bonds, if it's not other element, hydrogen. So just put the appropriate number of hydrogens to get yourself to 4 bonds. All right. All right, so as I mentioned, and as we saw, there's many different ways we could represent it. Most of the time, we're going to be using expanded structural formula and condensed formula and line structure and the molecular formula. Not going to probably be drawing too much ball and stick models or space filled or anything like that. All right, so here's again some formulas for butane. So this brings us to a really important point, which is sometimes people think, especially when we get to the idea of drawing something like isomers, for example, which are the same compound, but same molecular formula, but have a different connectivity. One of the most important things when you go to name an organic compound or try to figure out what the name is or what you're dealing with is you always want to find the longest continuous carbon chain. So that is really a very important part, is you want to find the longest continuous carbon chain. And what that means is you should start counting carbons on one side and keep going to the other side until you can't go any further. You kind of hit a wall. The only deal is you cannot back up. So it's like a one-way street. You go until you can't go any further, and that's how many carbons there are. Now, when you do longest continuous carbon chain, which we will do when we name things, is it does not necessarily always has to be the straightest. So sometimes people think it's always got to be like the one that's the straightest that you see. The longest continuous carbon chain could start like at the bottom, go up over this way, come back down, and so forth. The deal is you just got to keep going until you can't go any further and you hit a wall, can't back up or anything like that. So that's how you know, for example, if you drew something that is like the same molecule, or you drew something maybe that is a different molecule. So all of these guys down here, although they may all look different to you and drawn differently, they're all butane, and they're all butane because butane has 4 carbons basically. So if we look at the first one, it's pretty easy to see 1 carbon, 2 carbons, 3 carbons, 4 carbons. That is 4 carbons in a row. There's nothing else there but hydrogens. That's butane. Now, if you go below it, you may think, well, maybe that's something different because it kind of goes down and over to the right. But if we follow the carbons, 1 carbon, 2 carbons, 3 carbons, 4 carbons, that is still 4 carbons in a row. I didn't back up. I didn't hit a wall till the end there. That is still butane, even though it may look different. We come to the guy to the right. That is 1 carbon, 2 carbons, 3 carbons, 4 carbons, even though it went up, down, and over. Did not back up, and I still had 4 carbons in a row, which means it is still butane. Starting up on top, 1, 2, 3, 4. That is still butane. There is nothing else there. That was 4 in a row. 1, 2, 3, 4. That is also 4. This drawn straight down is also 4 in a row. And our zigzag, 1, 2, 3, and 4. So although they are all drawn differently, they are all still 4 carbons in a row. They are all still the same thing. It's just creative drawing, right? So yeah. So these are all butane. Now, let's say, for example, I had this. So this is all butane on the left here, right? And that is 4 carbons and 10 hydrogens. How many carbons do I have in this one that I just drew? There are 4 total carbons. How many hydrogens are there? There are 10. Is this butane? That is both answers. So one of those might be the right answer. So I hope so. So let's see. So the idea here is we're looking for the longest carbon chain that's continuous. What is the longest continuous carbon chain? It is actually only 3 here, right? You could get 3 by just going straight across 1, 2, 3, right? You could also get 3 by going straight across and hanging a U-turn up, right, as well. So they are both 3. No matter which way you go, you could only get 3. So the answer is this is not butane, right? This is 3, which, as you just mentioned, is propane, is the basis of this molecule. So as I was saying before, this is basically 3 in a row. We must take the straightest one there. That is only 3 carbons, which means the name of this guy is propane. And off of that main chain, we have like a branch happening there. And on that branch, we have 1 carbon hanging out. Yeah. That 1 carbon looked very much like the 1 carbon guy that is known as methane. But that's not methane because methane has how many hydrogens? 4. This one only has 3. This is what is referred to as a group that's attached to the main chain because it is not part of the main chain and it is actually missing 1 hydrogen. Why is it missing 1 hydrogen? Why can't I not just throw methane onto that guy like this? Throw the hydrogen. Why can't I do that? That carbon now has how many bonds? 5, too many, yes. So what is a group? A group, and this is what is sometimes referred to as a alkyl group. Basically a carbon-containing group is a fancy word for. It is a group that basically is the same thing as an alkane, except it is missing a hydrogen. And by missing a hydrogen, it allows it to connect in. So instead of it having 4 hydrogens, this group only has 3. But guess what? It is still named after methane. But this is a alkyl group, which means instead of methane, this is known as a methyl, YL group. Yes. And it has 1 hydrogen less, I think is what I'm trying to spit out there. It has 1 hydrogen less, which allows it to attach to the main chain without giving it too many bonds. Question on that. So back to this name, this is actually methyl propane. And as we will shortly learn in organic chemistry, it is all about location, location, location. Yes. So you need to tell people where you can find these groups. And to do that, we actually number the main carbon chain, which is the guy in green in my example here. And the guy in green, we can number 1 of 2 ways. We can number left to right, which means 1, 2, and 3. We could also number the chain right to left in this case, which is 1, 2, and 3. The way that you choose is you always want to, in the case of alkanes, when there are groups attached, the groups should always have the smallest number. Doesn't matter which way I go in this case. It really doesn't matter. But in some cases, it matters which way you go, depending on how you number it. No matter which way you go, that methyl group is sitting at carbon number 2, which is why that compound there is known as 2-methyl propane. Yeah. Which, long story short, that was a long story, but it is definitely not butane, even though it has the same number of carbons, it has the same number of hydrogens, but because of the way it's connected, the longest continuous carbon chain is only 3 versus 4, which was we see in butane. That is what is known as a isomer. And an isomer is the same molecular formula, but different connection. So both of these things, the 3-methyl propane and the butane, have exactly the same formula, exactly the same number of elements, but the way they're connected is different. And because of the way they're connected is different, 3-methyl propane has different properties than butane, and it also has different names. That is the best way, by the way, when you get to the part where you draw isomers, to know if you really drew an isomer or not, or you just made a pretty picture, is if you go to name two things that you drew and you end up with two different names, then they're isomers, provided you name them correctly. And if you end up with two of the same names, even though they may look different, then they are the same thing, just drawn differently. So as you can see here, if we went to name any of those butanes that were originally here in the table, they would all end up with the same name, regardless of the way they're drawn. But again, when we kind of move that fourth carbon to the center, now it actually did become something different, which is an isomer of each other. Any questions on that there? All right, so give the following expanded structural formula. Provide the molecular formula, the condensed formula, and the name. So let's take a look at this one here. Molecular formula, we just want to count up everything, right? So that is 1, 2, 3, 4, and 5. So that's 5 carbons. And if we count up our hydrogens on the outside all the way around, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's going to be 12 hydrogens. Something with that will be condensed formula. We basically just break it off by carbon units. So basically there, we would break it, and we would end up with CH3, which is basically this guy. CH2, which is basically that guy. CH2, which is this guy. And one more CH2, which is this guy. And CH3, which is that guy. Question on that there. Name of this guy's 5 carbons is? It is pentane, A-N-E. Yeah. Any questions on any of that there? Line structure would look like up, down, up, and down, I think here, right? So that would be 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. You typically don't put the little circles on it, but just to show you where the carbons are. Any questions on any of those there? Is 2 carbons, which means, again, if you follow the formula of this, 2 times 2 is 4 plus 2 more, which means it should have 6 hydrogens. That is going to be a CH3, CH3, basically. Again, the connection here is carbon to carbon with the hydrogens on the outside. Heptane, is 7. So that's going to give us 7 times 2 is 14 plus that. 2 more is 16. And again, if you're not sure, you could always just start with the carbons, 1, 2, 3, 4, 5, 6, and 7. And at this point, all you have to do is fill in the appropriate number of hydrogens, right? So guy at the end has 1 line, which means he needs 3 to get to 4. Guy next to it has 2 lines, which means he needs 2 to get to 4. Same thing with this guy, needs 2 to get to 4 bonds, 2 to get to 4 bonds, 2 to get the 4 bonds, 2 to get the 4 bonds. Guy at the end has only 1 line, which means he needs 3 to get there. So that's a very common way when we start drawing things to do it as well. Kind of just start with the carbons and then fill in the hydrogens to get everybody to 4. Any questions on any of that there? All right, so let's talk a little bit about cycloalkanes. Cycloalkanes are alkanes where, frankly, the ends come together and they kind of join, and they make pretty little shapes and stuff like that. Cycloalkanes actually have a formula of CnH2n, no +2 on them, so they missing 2. Why are they missing 2? Well, if we take something like our friend propane here, CH3, CH2, CH3. These two guys are going to come together, but as is right now, if you try to make a bond between those two, they would end up with too many bonds. So in order to make that bond, we actually have to lose some hydrogens, and we will end up with something that looks like this, that has 3 carbons and 6 hydrogens. These are typically ones that make geometrical shapes, like a triangle and line structure, a square. Go look at like this. So this is a 3 carbon, 4 carbon, 5 carbon ring, and 6 carbon. How do we go about naming guys that are cycloalkanes? You put cyclo in front of the name. So that is 3 carbons, which means that's propane, and it becomes cyclopropane. That is 1, 2, 3, 4 carbons, which is butane, and a ring structure that would be cyclobutane. That is 6 carbons, 1, 2, 3, 4, 5, and 6. That is hexane. This would be cyclohexane. And lastly, over here, 1, 2, 3, 4, and 5 carbons, which is pentane. This would be cyclopentane. So if it's a cycloalkane, it means that basically 2 carbons came together. In organic chemistry, pretty much anytime you make a bond, an extra bond, you have to sacrifice 2 hydrogens. And 1 hydrogen from each carbon is pretty much where the sacrifice comes from. So otherwise, you will have too many bonds for everybody. So always when you pop on, for example, a double bond or a triple bond, every time you do that, 2 hydrogens disappear. 1 from each of the carbon where that extra bond is coming in. In this case, since we're kind of closing in the ends together to make these ring type structures, we lose a hydrogen at each of those carbons that come together to kind of close in a ring structure. So every time you make a bond, an organic, you lose 2 hydrogens, 1 from each carbon. All right. Any questions on that there? Okay, we're going to continue on here. So as we just were talking about, these are cycloalkanes. Once again, they will have 2 hydrogens less than the straight chain alkane because they came together to make that bond in more of a ring type structure. And most of the time, I would say they are drawn like we see here at the bottom in their line structure form. And again, that's how you would do them in their condensed structure form. And you probably never have to draw the molecule in type shape. Yeah. It's sometimes people will write it that way to emphasize that the connection is through the carbon rather than writing CH2 to CH2. And sometimes people will do that, and they'll do it in condensed structure as well. It's kind of the hydrogens on the outside. I'm okay with you doing it either way, as long as, again, you understand that the connection is between the 2 carbons. Yeah, so that's the important part. But you will definitely see people sometimes do that. All right, so we've been kind of doing these. So let's just take a look at these together. We want to name this. So this is, again, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. Once again, here we're looking for the longest carbon chain that just keeps going. That's everything pretty much. So that's definitely going to be 8 carbons is octane. They are all single bonded. Not drawn here. If there was a double bond, you would see it actually drawn like so. Yeah, so it'd actually be drawn into the structure. But obviously we don't see that here. So we know it's all alkanes. When we look at this guy, we can also look for the longest chain. And in this case, it is just around the circle here. So that's 4 and 5. So that's based off of pentane, but it is a ring type structure. So this then would become cyclopentane in this case, right? Any question on either of those two? Yeah. We're going to actually talk about that in just a second. We'll get to it. Yeah. Other questions? Okay. So let's take a look at these, which I think we might have done along the way. Here we got 1, 2, 3, and 4 carbons. Nothing else there but hydrogens. So that's going to be our butane, which is 4 carbons. This is a cyclic structure where we have 3 carbons there, which is based off of propane. Once again, it is a cyclic or ring type structure. So that's going to be cyclopropane in this case. Here, just counting 1, 2, 3, 4, 5, 6, 7, and 8, all in a row. They're all hydrogens, nothing else there. So that's going to be octane. And once again, here, just counting around anywhere where lines come together will be a carbon. So that is 6 carbons. So that really is based off of hexane. Hexane, though, is the straight chain of that. Here, the ends sort of come together, and it makes this cyclohexane. By the way, cyclohexane, what we see here, has no double bonds. A ring that looks like that with double bonds is benzene, and that is different than cyclohexane. So something with no double bonds and that type of ring structure is definitely cyclohexane. Any questions on any of those there? God. So let's talk then about substituents and things that are attached to these main chains and how we go about naming it. And we'll get to your question as well in terms of what happens when we start adding some things to those guys. So a substituent is basically when we have something that is basically attached to the main part of the chain. So as I mentioned earlier, when you're doing any type of naming with organic chemistry, it's all about finding that longest continuous carbon chain, whichever way it goes. And usually a good rule of thumb is kind of what I did with the other one, kind of put a line, a box around it, highlight it, and then anything that is not part of that longest continuous chain is what's known as a substituent or a group that's attached to it. And as we saw with that methyl group, it is named a little bit differently if they are a group versus how we would name it if they were part of the main chain. So as we also saw, we have isomers, which are structural isomers. And once again, isomers have the exact same molecular formula, but they have different connectivity, which gives them different properties. And one of the best ways, as I mentioned earlier, to sort of figure out, did you draw an isomer or not, is to actually name it. So I think we're going to kind of combo all this together as we talk about isomers and naming. We're going to put them together so we can see how it all works together here so that we properly name things. So as we saw with our butane, the 4 carbons straight across, 1, 2, 3, and 4 is butane. Once again, here, that was the one we drew earlier, the 2-methyl propane, which only has 3 carbons as its longest carbon chain. So let's talk, before we do that, let's actually talk a little bit about substituents and how we go about naming them. So there's a couple different types of sort of groups that you will find attached to these longest carbon chains. There are some that are referred to as alkyl groups, and these are really carbon-based groups. And these are pretty much like your 10 alkanes, as we talked about, except missing 1 hydrogen that allows it to connect in. And because of that, they swap out the last part of the alkane name and you put YL there. So for example, as we saw with our 1 carbon group, that is a methyl group based off of methane, missing 1 hydrogen. If I had a 2 carbon group like this, 2 carbons with all the hydrogens is CH3, CH3. That is ethane. missing one hydrogen that allows it to connect to this carbon, and that is going to be what is known as a ethyl group. And you can do that for any of those. You can do that for propane, which will give you a propyl group. Now, it does depend, and it does happen, for example, when we look at propane, for example. We look at propane, look something like this. And when we look at carbons, this is propane. When we look at carbons, there are different ways that you can classify carbons. So you could have a carbon which is known as a primary carbon. You could have a carbon that's known as a secondary carbon with a little 2 symbol, and you could have a tertiary carbon, which has the 3 with a little dot symbol. What is the difference between them? It is pretty much you take the carbon that you're looking at and you find how many carbons are directly attached to it. So very simply, I have a carbon like this that's attached to one other carbon, and I'll say all these are hydrogens. This carbon is attached to only one other carbon. That makes this carbon a primary carbon. Yeah. So that's as simple as you could get it. Yeah. So you look at the carbon you're looking at, and you want to see how many carbons are directly attached to it. As you might imagine, if I had something like this carbon right here is attached directly to 1 and 2 carbons, which means that this carbon right here is a secondary carbon. Yeah, so 2 carbons attached to it, secondary. I'm sure you could probably imagine, but this carbon right about here would be a tertiary carbon, as it is 1, 2, and 3 carbons attached to it. This would be a tertiary carbon. So we classify carbons as primary, secondary, or tertiary. I personally think looking at the carbon and seeing how many carbons are attached to it is the way to go, because it's the same as the number. But some people teach this as how many hydrogens there are, which would be sort of opposite. So in a primary carbon, you would have 3 hydrogens, which again might confuse you. So I personally think carbon to carbon is the way to go, because 1 carbon to 1 carbon is primary, 2 carbons to 1 carbon is secondary, 3 carbons to 1 is tertiary. But just so you know, some people will teach it as to how many hydrogens there are attached. Personally, go with the carbons. It's just I think it relates to the number, so you might as well just do it that way. Is the best way to do it. So why do I care about this? I'm not sure, but why I care about this is probably for that propane I drew up there. When we look at propane, it's having bad flashbacks. It's all right. All right. So we got this organic flashbacks. There we go. We have some different carbons in this case, right? So let's start with the carbon here on the far left. Is that a primary, secondary, or tertiary carbon? How many carbons are directly attached to it? 1, which means it is a primary carbon, yes? How about the guy in the middle? How many carbons are directly attached to that guy? 2, which means what type of carbon? Is a secondary, yes? Carbon at the far right is a primary. There's only 1 directly attached to it. So even though there's multiples, it's got to be directly attached to it. So here there's only 1, which makes it a primary. Any question on how to identify the different types of carbons? So why this is important, a good question. So why this is important is when we get to groups, sometimes some of the alkyl groups, their name is based on how it attaches to the main chain and through which carbon it attaches to the main chain. Now, for example, if I took a hydrogen off of the carbon on the left or the carbon on the right, which are both primary carbons in the case of propane, you get what is referred to as a propyl group or an N-propyl group, a normal propyl group, however you want to call it. And we would have the attachment point, for example, here at the end carbon. Left end, right end. This is where it would attach to the actual chain. And that is what is known as a propyl group. and that is a primary carbon that's making the attachment. Now, if I took a hydrogen off the center guy, that is a secondary carbon. And that would actually give us a group that looks like this, where the attachment would actually come in the center there. And that attachment in the center is actually a secondary carbon as to where that comes from. Because of where it attaches, it actually has a special name. This is what is known as isopropyl group. That is a historical name that's used a lot. It is basically CH3, CH3, where the attaches right there at the carbon and the secondary carbon. But if you attach this propane group to the end, it is a normal propyl group and it's just called propyl. So sometimes that happens. This table has some of the different types of groups. Again, propyl, there's our isopropyl. There's also one that's sometimes referred to as T-butyl. T would mean tertiary. It's going to attach to the tertiary carbon. So there are some groups that have historical names that are based off of what carbon's doing the attachment for the group. I say for us, isopropyl is really the one that you should know. It's probably the one that will come across. But again, if you see something like T-butyl, it means that it's attaching through the tertiary carbon in that butane group. There's also one called sec-butyl, which would be attaching through the secondary carbon. So there are some names that come from how those groups sort of attach. But if you're just simply taking off an end carbon, the hydrogen, and that's how it's attaching, you basically just take the alkane name and put YL at the end of it. And again, an ethyl, propyl, butyl, pentyl, and so forth is how they attach. But again, if you get some of the attachments that happen kind of in the middle of those groups, they might have some historical names. I say for us, like I said before, this is probably the one you should watch out for. It probably will pop up. Now, in addition, which was the other part of that slide, I think on the previous, is that we can get some halogens involved as well. And when halogens are attached, we name them the similar way. Fluorine is the fluoryl group. Chlorine is the chloral group. Bromine is the bromol group. And iodine is the iodo group. And that is just the way that we name halogens that are sort of involved along the way. Any questions on groups? No? All right, so now that we kind of got our groups, let's draw some isomers here, and then we're going to actually name them so we can see how naming works and putting everything together, and then we will all be professionals. All right. So why don't you start now? First, draw 3 isomers of pentane. So 3 different isomer structures that have 5 carbons and 12 hydrogens. And you're looking to make different structures, not the same one. So see what you come up with. I will think. Okay, let's take a look. So clearly the one I drew here is pretty straightforward. Might just do 5 in a row. Seems like a good idea. So why don't we do maybe not 5 in a row, but we'll do like 4 in a row. Maybe move it over here. I'm gonna fill in my hydrogen. So that one needs 3. That one needs 3. This one only needs 1. This one needs 2. This one needs 3. Maybe 3 in a row, maybe something like this, perhaps. Those 2 there, necessarily 1. Again, I'm filling in hydrogens to get to 4, so this one needs 3. Maybe something like fill in some hydrogens here. That one needs 2, that needs 2, that needs 3. Maybe all right, so I drew a bunch of different ones. They all, hopefully, if I didn't mess up, They all should have 5 carbons and 12 hydrogens, each of them. So we want to know, did I draw a bunch of isomers or did I screw up? So we're going to name each of these, which is really probably the best way to know whether or not you did draw sort of an isomer or not. Again, if you end up with really the same name, you didn't draw an isomer. If you end up with some different names, again, if you named it correctly, you did. So how do we go about naming? So we talked a little bit about it a second ago, but here's pretty much the steps. We want to count or find the longest carbon chain. And again, that is the longest continuous carbon chain. Again, as we talked about, you just can't go backwards. You got to go one way or the other. You also want to, when you're doing that, sort of check all of your options to make sure you didn't miss one. Again, it doesn't have to be the straightest. Once you do that, you want to find the groups that are attached to it. You want to number the chain to give the groups the smallest number. You want to go groups in alphabetical order, followed by the base name. And there's a few other things along the way that we will kind of fill in as we go through it so you can kind of see it in action. Let's start with the very first one I drew, which is just 5 straight across. I don't think I can screw up on that one, hopefully, but we'll go. Longest carbon chain is 5 straight across. And there is nothing else attached there. Everything else is hydrogens. So clearly 5 straight across here will be pentane will be the name. Yeah. So that's a good start. We got one name. Yes. All right, let's take a look at the next one here. Longest carbon chain on the one below it is how many? It is 4. You could get 4 by going straight across. You could also get 4 by going straight across and up. It doesn't matter which way you want to choose. So I would recommend taking the straightest because it's just easier to see, but you can choose either way. They will all get you the same name. I'm going to take the straightest as my longest continuous carbon chain. That means group-wise, what I have attached is this guy right there. So starting with the base of the name, something with 4 carbons is butane, right? So that is the base of the name. We now want to look at the group that's attached. That is a 1-carbon group, which is based off of methane, and it is an alkyl group, which means this is a methyl group, 1 carbon, yeah. Now we have to give the location of this group. So we can number the main chain, which is in green here, one of 2 ways. We could go left to right, which means 1, 2, 3, and 4. We could also number right to left, which is 1, 2, 3, 4. We want to go whichever way gives the group the smallest number. Which way gives it the smallest number? Right to left. So we would want a number in this case in this direction because it gives that group a smaller number, and it is as simple as 2 is smaller than 3. Yes, when you're just trying to decide that. So that is 2-methyl is what that is referred to. And we go 2-methyl. The 2 is the location, the carbon where the methyl group is found. We always do a dash between a number and a letter. And that is all that's on there. So that is the name. We'd start with the group, which means that this guy would be called 2-methyl butane. That basically tells us at carbon number 2 of butane, there is a methyl group hanging out there. It's basically what the name tells us. Yeah. Question on that. So always a dash between a number and a letter. So we always do a dash between a number and letter. By the way, if it happens, we do between 2 numbers, a comma between 2 numbers, in case you have that. We do alphabetical order of the groups, regardless of prefix. So what do I mean by that? if you have the same group in that compound in multiple places, you use prefixes like di, tri for 2, 3 of them, and so forth. So you ignore those prefixes when you're doing alphabetical order. Also, you ignore the number. So if alphabetically your A has a higher number than your B, you go with your A, regardless of the number. So it's based on alphabetical order of the actual group. I don't make up the rules. Again, send your comments to in care of IUPAC. They're somewhere in Europe, I think. All right. So first off, did I draw 2 isomers in those 2? They are. They're different names. They're different connections. They are 2 isomers of each other. So that's good so far. Let's hit the next one, which is, did I draw an isomer here? Let's see. Longest carbon chain is 1, 2, 3, and 4. Also could get it 1, 2, 3, and 4 if you went down, right? So it don't really matter which way you go. All right, so let's see what I did here. I don't think I did good here on this one. So that is 4, which is the longest carbon chain, which means our base of our name should be butane here, right? We have one group attached right here, which is a methyl group. We want to number this, which can be numbered 1, 2, 3, and 4. Or we can number this going the other way as 1, 2, 3, and 4. What number should that methyl group get here? Which one's the smallest? It is the 2. Yes, we would number actually going in this direction, which means that is 2-methyl, which means the name of this guy is 2-methyl butane. Did I draw another isomer? I did not, even though it looks different. But it is the same thing, just turned around. It got lost, it got turned around. Not so good, yes. So unfortunately, I wasted my time there. That is not an isomer. So I was kind of hoping it was, but it's not. That's all right. So this is how you can see, right? If you name it, you get the same name, even though it looks different, right? Sometimes that's what happens when people draw isomers. They're like, I'll just like move that up, move that down, and it's really the same thing. You just kind of moved it. All right, let's see if I salvage the rest of it. I'm not very confident. Let's see here. All right, coming here to the right, longest carbon chain is 5. 1, 2, 3, 4, and 5. The name of that's going to be pentane. Is that an isomer? It is not either. It's the same thing as my first one. I just drew it funny looking, right? So that is not an isomer either. How about my last one? Longest carbon chain is 1, 2, 3, 4, and 5, which means the name of that guy is pentane as well. Is that another isomer? It is not. So I successfully drew 3 pentanes without trying. All look different, right? All you might have thought were isomers, but they're not. They're all just the same guy, just drawn differently. And I drew 2 of 2-methyl butane, which I didn't really intend to do, but I did actually. So let me need one more isomer here. So let me get rid of some of the garbage I drew over here. That's why they invented erasers. Let's try this again. All right. So clearly, I shouldn't draw the same thing again. So clearly, maybe in this case, we want to go 1, 2, and 3. And maybe we attach some carbons right there to the center guy. And now we put some hydrogens on. So that one needs 3, that one needs 3, that one needs 3, that one needs 3. The guy in the center needs none because it has 4 bonds. Now I got something that looks even better, maybe different. I don't know. We'll see. Let's name it and see if we actually did better than our bad job here on the rest of them. All right. So looking at this one here, longest continuous carbon chain is how many? It is 3. You could get it multiple ways. You could go straight across. You could also go straight and up, or Even you could go from the middle, just straight down, right, and get all three. So 3 is the longest, so that's looking good so far. 3 carbons is propane, right? So that is the base of the name. So that sounds different than all the ones we had previously. So maybe we're doing better. We actually have 2 groups in this case. I got me a group right about there, got me a group right about there. Those are both methyl groups, right? They're both 1 carbon groups, which means I have a methyl group up there on top. And I have a methyl group down here on the bottom. And by the way, that is 2 methyl groups in the same compound. Happens to be on the same carbon, but does not need to be on the same carbon. As long as you have more than one, in this case, we're going to use the prefix. So that's actually like a dimethyl situation happening there. Di for the 2 methyls, again, not because they're on the same carbon, but because they're in the same compound. So they can be on the same carbon, they could be on different carbons. They would still be called dimethyl because there's 2 of them in there. We need to give some location, which means we do need to number this guy. And it doesn't really matter which way you go. Those methyl groups are going to end up at carbon number 2. And because there's actually 2 different methyl groups, you need to give the number for both of them, which happens to be the same number, which means this would be 2, 2, comma between 2 numbers, dash dimethyl. That is basically saying at carbon number 2, you can find both methyl groups, right? One at carbon 2, the other one at carbon 2, and propane to end out my name there. Yes. 2, 2 dimethyl propane. Question on that name there. Is it an isomer? Thank goodness it is an isomer, right? I'm out of paper here on this line there. So as you can see, sometimes people just mistakenly, when they're asked to draw isomers, they're just like, I'll just kind of draw it looking different. And they end up actually drawing the same thing, just it looks different. So that is really the best way to know whether or not you really did draw an isomer or not, is to put the correctly part of that, correctly name everything. And if you end up with different names, then you probably did draw different isomers. Again, if you end up with the same name like I did there, and by the way, I honestly thought I drew an isomer there on the bottom left, and it wasn't when I went to go name it clearly. So it happens even to me, you know, sometimes you draw it and you go, that looks different. And that's a really good way, again, to sort of, I don't know if you did or not. Question on isomers, naming, yes. Yeah, so let's do one where we have a couple of different things attached. So let's take a look at one here. Let's do actually do let's do this right here. Why not? That looks like fun. I don't know. Maybe not. Let's do that. Let's add some hydrogens. All right, let's see here. Let's have the right amount of hydrogens. Like I know chemistry, maybe like that. All right. Give it a go. See what you come up with on this one, and we'll talk about the naming here in just a second. I'm going to do it as well and hope for the best. Let's see. Okay, let's take a look. So longest carbon chain here is 6 is correct. So that is 1, 2, 3, 4, 5 only. That is 1, 2, 3, 4, 5, 6, if you kind of come up that way. So remember that when you are looking for the longest continuous carbon chain, it may not always be the straightest. And again, you just want to go one way, 1, 2, 3, 4, 5, and 6 until you hit a dead end. So in this case, that is actually the longest continuous carbon chain, which is 6. That means the base of my name, since it's all single bonded, would be hexane, right? Which goes with my 6. I then have a couple of groups that are hanging off of this. I have a 1 carbon group here, which is our methyl group. I also have a Cl here, which is a halogen, so that is going to be a chloral group. Any questions on that so far? What's left is the numbering part of it. So we can number left to right, 1, 2, 3, 4, 5, and 6, which means as we go left to right, we have a group at 2 and 4. If we number right to left, 1, 2, 3, 4, 5, and 6 in terms of the carbons, we would have groups at 3 and 5. The one that is the smallest number is going left to right. It's this way. And it is as simple as 2 is smaller than 3. That's basically all you have to look at is basically 2 is smaller than 3. And that is the way that you want to go. So now that we have our numbering in place in terms of which way we want to go, I'll get rid of the numbering coming this way as we do want to go the other way. We know that our chloral group here is going to be 2-chloral. Our methyl will be 4-methyl. So to answer your question, alphabetically in this case, it should be the chlorine before the methyl in this case. So we want to go C before M. And again, that's regardless of the number. So for example, if by some chance the chlorine here had a 3 and the methyl had a 2, we would go still with the chlorine first. So we want to go always with the letter. If we had a prefix, like we had another chlorine in here and it was dichloral, we would not, you look at the di part of it, we would look at the chloral part for alphabetical as well. So regardless of prefix, it is always just the first letter of the group that's there. And regardless of number, it just goes alphabetically. Yeah. So that means putting this together, this would get us a 2-chloral dash 4-methyl. Again, we want dashes between numbers and letters. And then we could end it with hexane. So this would be 2-chloral 4-methyl hexane. It's all about the location of where we can find those groups. The 2-chloral means go to the second carbon on hexane, and there's a chlorine sitting there. The 4-methyl means go to the fourth carbon on the butane hexane, and there's a methyl group sitting there. So it's all about basically telling people where you can find things. Question on that one there. To answer the question about the cycloalkanes, let's say we have this guy by itself. That is 4 carbons, which is cyclobutane, right? Now, if I take this and I put a line, yeah, that is still cyclobutane is our longest carbon chain. What does a line mean? It is a methyl group because at the end of that line is a carbon that should have 3 hydrogens, right? So if you just see a lonely line, it's actually a methyl group. If it needs something else there, they will write it if it's something else. If not, it's a methyl group. So this is known as methyl cyclobutane. It is no number is needed in this case because this is what is referred to as being monosubstituted. There's just one guy that's on the ring, and wherever that guy is on the ring, it's assumed to be carbon number 1. So because there's just one group, you do not have to give the number. So this would be just methyl cyclobutane. Now, if I take something like this and maybe something like that, now I feel like I'm just putting squiggly lines, and I might be, but this is still cyclobutane, right? It's the square. I still have this guy, which is a methyl group, right? This group right here has how many carbons? It does have 2, which means it's a ethyl group. Now I have multiple things on this guy. Do I need a number, you think? I do need a number here. Now we're going to default in our rules, right? We can basically do 1 and 2, or we could do 1 and 2 going in that direction. Which one do you think should have the lower number? Yeah, because we can default to alphabetical here, and we have an option. So giving the E the smaller number would make sense than giving it the bigger number in this case. So we would probably want to number this in this direction here, where we go 1 and 2, and we would put that together. That's going to be a 1-ethyl dash 2-methyl and our big name there of cyclobutane. Any questions on that? So if you have a cycloalkane where you have multiple groups attached, you do need to give the number. And because you could kind of go around clockwise, counterclockwise, it doesn't matter in this case because there's no double bonds. You would probably want to give whichever one alphabetically the lower number if you have that option like we did here. Question on how to name those guys. All right, so I want to finish up with talking about probably the easiest thing to do, which is to actually draw these things from the name. And sometimes people think that's like the hardest thing because you got to draw it, but it's actually relatively easy. I'm just going to make up a random name and hope for the best here. Let's do, I don't know, let's do, let's do 3-bromo 6-methyl. Oh, I'm gonna regret it. It says it's not here. 6-methyl. Go with octane. So we want to draw this guy right here, and you have the name given to you. So when you go to draw, you should always do this. Just go to the next question. No, I'm just kidding. You should always. Thank you for not laughing. All right, so you should always start backwards and work your way backwards in this case. And what we want to start with is octane. So that tells us it's how many carbons? 8. So that's really all you want to start with is just the carbons, nothing else. So we're just going to start with the carbons, which is 8. 1, 2, 3, 4, 5, 6, 7, and 8. Why I regretted it a second ago. So that is octane. I'm going to cross that out. That means I have 3-bromo and 6-methyl. That means that at carbon number 3, there's a bromine group, right? And at carbon number 6, there's a methyl group. Because you are drawing it yourself, you can number left to right or right to left. I'm going to call this guy right here carbon number 1. You could call the other side carbon 1 if you wanted to. That means for me, that's carbon number 1. Next to it would be 2, 3, 4, 5, and 6. And at carbon number 6, there should be a methyl group. That takes care of that, right? That means at carbon number 3, since I already started numbering left to right here, carbon number 3 would be right about there, which means there should be a bromine group. I have crossed out the entire name, which means everything else there should be hydrogens, just to give carbon 4. So if we look at the end, that guy has 1 line. He needs 3 to get to 4. Guy next to him has 2 lines. He needs 2. The guy next to it has 3 lines. He needs just 1 hydrogen. Guy next to it has 2 lines. He needs 2. 2 lines needs 2. 3 lines needs 1. 2 and 3 here. There it is. Yes. Always work backwards. Start with just the carbons. Add in everything else. Question on that there. All right. Why don't you try one here? Let's do 2,4-dimethyl hexane. And why don't you draw propyl cyclopentane. All right, draw each of those structures there. Again. Okay, so since we're getting there, let's take a look. So we want to again start backwards. So hexane tells us it is 6 carbons. So that is all you want to start with is the 6 carbons. That is 6. That takes care of that. At carbon 2 and carbon 4, dimethyl means that each of those carbons I have a methyl group. So I'm going to call this carbon 1 for me again. That means at carbon number 2, I should have a methyl group. And that would make that carbon number 4. I should have a methyl group. Once again, at this point, everything else is going to be hydrogens. So we're going to do 3. We're going to do 1 to get to 4. We need 2, 1, 2, and 3. Again, we're filling in hydrogens to get carbon to 4. So however many hydrogens you need based on how many lines it has is how many you need to get to 4. Any questions on that one? Lastly, here we'll do the same thing. That is cyclopentane. That is the ring structure as the 5 carbon. If you did line structure, it looks like that. If you did not do line structure, it looks like this. More of expanded structure. Propyl means I need a propyl group, which is 3 carbons. It doesn't matter where I put it. It doesn't, because wherever I put it, it's going to be carbon number 1. So I'm just going to put it right on the top, and I'll just do 1, 2, and 3, running right into that. Again, you could also have done a little line structure if you want. Probably on the line structure would have been better, but you know, you could put that in there. So maybe so it's not so squished. Any questions on how to draw it? You always want to start backwards. You always just want to start with the basic carbon guys, and then basically fill in all the groups and then add the hydrogens. That was fun.